Well, welcome back, everyone, or should I say, welcome back, Patreons. We're picking back up with our HFR learning series. When we last left off, it was on DC circuits, and now we're going to get into AC circuits. However, there's going to be a slight change to the methodology in which I present to you this material, primarily because I was in somewhat of a rush to get out the initial training for DC circuits that I made content that was rather long, to be honest. So I want to condense some things down and offer content in a more suitable sit and watch approach. I mean, these videos are going to be shorter in length. They're not going to be an hour long. We're looking at hopefully around a 20-minute mark. With this first video in AC circuits being a soft introduction to everything else that we're going to learn. Does that mean that this video should be skipped? I would hope you wouldn't skip it, because there are some things that we will do in this video that will have demonstrative purposes that you can follow along with. That being said, let's get to it. Well, in an attempt to make this a slightly more professional learning experience, what I've done is develop slides in which we can progress along. So I'll open this up with the question, what are alternating quantities? Well, in consideration of that question, the electrical quantities which vary or change continuously with time are known as alternating quantities. Alternating voltage and current are some of those quantities. The magnitude of these alternating quantities changes continuously with time, and the direction also varies or changes after a definite time period. As you can see on these pictures here, this is representative of, say, an AC voltage, whereas this bottom line could be representative of a DC voltage or an absolute zero. Okay? So with alternating voltage, or AC voltage, we can see that it changes over time, and that the polarity also changes over time. So in one instance, we get a more positive voltage. Then as time progresses, we go more negative. No different than our current swapping around as depicted over here by this little video. However, these alternating quantities have different types. These alternating quantities may have square waves, triangle waves, sawtooth waveforms, and sinusoidal waveforms as an example. More commonly, when I'm speaking of sinusoidal waveform, as you see me state in many of my videos, this is the waveform that I'm commonly referring to. When an alternator produces AC voltage, voltage switches polarity over time as previously stated, but does so in a very particular manner. When graphed over time, the wave traced by this voltage of alternating polarity from an alternator takes on a distinct shape. This is known as a sine wave. These waveforms are by no means the only kinds of waveforms in existence. These are simply a few that are common enough to have been given distinct names. However, there are some other waveforms that I've mentioned in several of my other videos, especially when I'm working on audio equipment. You often hear me talk about symmetry. Well, depicted in this picture are asymmetrical waveforms. And how do we know that they're asymmetrical? Well, if we were to put them onto an oscilloscope and graph them over time, we would be able to determine, such as with item A, that the amplitude starts to shift upward. See that shift above the gradical? Top gradical going upwards, below one going up, more north. So we could say that this sine wave is asymmetrical because its amplitude is asymmetrical in relation to its center or absolute zero voltage, point in which the voltage is at a null. In item B, we could say it's asymmetrical because our peaks are not symmetrical, no matter where they're plotted on the positive or negative slope of its waveform. See, they diverge quite a bit in their symmetry. And C and D are also examples of asymmetrical waveforms. Now, they could still have equal amplitude, and with a digital multimeter or analog multimeter, you might measure the same AC voltage, but that voltage could be dirty, and you could have an asymmetrical waveform like this, like these examples. However, not necessarily are all asymmetrical waveforms bad. For instance, when I'm working on, guitar amps, they have the ability to, or some have the ability to shape the waveform through a shape matrix or overdrive or distortion. And when you shape those waveforms, this is essentially what you're making, is you're turning that nice sine wave into something that's asymmetrical. However, generally speaking, when it just comes to amplification, whatever waveform you put in, you want the same exact waveform out, just at a higher amplitude. Thus, we will also talk about distorted waveforms. Here's our first example. Let's say our input signal looks like this sine wave right here, and we expect our output signal to look like this sine wave down here. See, it's at a significantly different amplitude. However, when we take our oscope and we probe that signal, instead of seeing the before and the after, or input and output, instead we see something that looks more like this right here. Well, what has caused that? Distortion has caused that. And if we were to filter out our input signal, we would see that distortion as displayed down here. Also annotate as the peaks on this distortion how they affect the negative peak of our audio signal. See how they line up? And again, because let's say we're using an oscilloscope, the range that we select for our amplitude is also going to play a significant role. If I don't have this scaled per division correctly, I could be looking at amplified output like this and think maybe it's a good reproduced input signal, but it'd be hard pressed to tell if there was distortion on this lower peak. In the same way, I could just be seeing the distortion alone and not the input signal, and thinking that that is my signal coming in. But it would not be, because we could tell that this distorted signal has a lot more cycles over a less period of time than our input signal. So those are things that we have to annotate. Here goes another example. Notice again our input signal and our undistorted output. This is what I'm sending in, and this is what I want to see at the output being amplified. Notice again we have a distorted signal that's being applied to our input signal. And once that distorted signal is applied, then our outputted amplified distorted signal looks like this. Notice also again, as these negative peaks line up to the positive peaks here, what occurs with that distorted signal. And again, as previously stated, if your oscilloscope is not set correctly, you would be hard pressed to determine if that signal is distorted or if you're looking at your input signal or just distortion alone. So just a couple things to keep in mind. The question now is, well, how do we know the signal that we have if it's good or bad? Well, as demonstrated over the last few slides, one area of application is visually inspecting this signal, which you can't do with a handheld multimeter, but you can do with an oscilloscope, so long as you know what the input signal should look like and what the output signal should look like, not just in amplitude, but also in frequency. And the other way is by measuring the voltage. Voltage? Well, what do you mean by voltage? Are AC voltage measurements no different than DC voltage measurements? Well, if you think they are, you would be incorrect. There are actually multiple ways to measure AC. We will cover that next. The first way you measure AC is with a peak-to-peak measurement. As depicted on this slide here, you're comparing the difference between your positive and your negative slope at the highest point of amplitude, and the difference between the two would be your peak-to-peak voltage, typically abbreviated VPP. Sometimes abbreviated also as VPK to PK. Well, there goes one example of how to measure AC voltage. What's another? We have peak voltage. In peak voltage, you're only concerned about one peak, either on the positive slope or the peak on the negative slope. Why do we care about a peak measurement? Well, if our peak to peak is 20 volts, but our single peak measurement is showing 9 here instead of 10, and 11 here instead of 10, then our signal could potentially be not symmetrical. Which is also why it's important to set up your oscilloscope correctly so you don't come to that conclusion. But in a peak measurement, as stated, you're only concerned about 1/2 of the sine wave. And then the difference in between the amplitude of where your null reference or zero VDC is at in relation to where the positive amplitude of your VAC is at. So hopefully that makes sense. And if you're digging into technical data and it's asking you to verify a peak voltage, typically abbreviated as VPK or Vmax. Then we have average voltage measurements, typically abbreviated V, then lowercase av. The average value is actually a mathematical equation conducted by measuring your V peak, meaning 0 to upper end, and then multiplying that by 0.637. And that will give you your average value. And you can see by this picture here, the depiction of these dotted lines, which would represent what your average, voltage would be, or where it would be. So you can say that it is a measurement significantly lower than what your peak and even your peak-to-peak measurement would be. Okay, is there another way we can measure it? Of course, RMS voltage. An RMS measurement, typically root mean squared, typically abbreviated VRMS, is a measurement of your peak voltage times 0.707. That average is slightly higher than your voltage average measurement, and thus displayed on this graph as a dotted line a little bit above. So how is this applicable to us between all these different types or forms of measuring AC? Well, generally speaking, your technical data, or your technical guide, or whatever you're using in order to make your measurement is going to tell you what you should be measuring in what format concerning the AC measurement. Meaning, it's going to tell you that you have to measure this value in a peak-to-peak or a peak or volt RMS or volt average fashion. However, if depending on the tools you're using, you may only be capable of measuring volts peak-to-peak or volts RMS. In general application, if I am using an oscope, I can get my peak-to-peak measurement and my peak measurement And then from there, use these formulas to calculate out my volts RMS or volts average. However, if I'm just using a digital multimeter, typically they only produce either an average measurement or an RMS measurement. You would need to consult with your voltmeter or digital voltometer, multimeter, the book that came with it, to determine what measurement it's providing you. Thus, you need to also understand that volt RMS or volt average that your digital multimeter or analog multimeter is providing you is going to be a significantly lower value than what you would measure on the oscope if you were going peak to peak. Now, what if your guidance, your technical instruction, or your manual doesn't tell you what you should be looking for here? Well, typically, if it's at least saying on your oscilloscope, verify your AC measurement, is probably referring to a volt peak to peak. But if it's asking you to use a digital multimeter or analog multimeter, typically, I would assume that it's volts RMS, unless otherwise stated. And if you stay to those two generalizations, you're going to be fairly safe. Generally speaking, when you perform AC measurements or looking at a value under test, you need to know what measurement type you should be seeing for the voltage you are obtaining. The oscilloscope is used to display voltage or current variations with respect to time or related electrical signals. Why don't we move to a demonstration? In this demonstration, I have my signal generator coupled to my oscilloscope directly via BNC cable. I have set my SIGGEN to a 1 kHz audio tone at 5 volts amplitude. And then over on my oscope, if you recall from where I taught how to use one, I'm going to ensure that I first couple to the ground and set my reference where the X and Y axes meet at their absolute 0 point. Then I'll change my coupling from back to AC. Now I'll take a quick note when I switch to DC. It might look like it's correct, but watch the subtle shift when I go to AC. Did you see it? Hopefully you did, and you don't make the mistake of keeping your coupling to DC when making the AC measurement. Now I'm going to make a manual measurement. For that, I go to the cursors, turn it to manual, type. It's going to remain at voltage. And then I should be able to take cursor B. We'll put it at the very top here. And I'll switch over to cursor A. And we'll move it up to the center. There we have our peak measurement of 2.42. Our peak to peak measurement of 4.78. So we're slightly below 5 volts with the manual measurement. And if 2.42 was the upper peak, let's see what the lower peak is going to look like. It should be symmetrical. Let's see. Well, I misread the first thing. Yeah, 2.38. Apologies. We change channel B. Let's see if we're at 2.38 once we go below. Yeah, we're practically there. Yep. 2.38 above and below. There you go. That's a perfectly symmetrical waveform. And again, if I needed to know the RMS measurement, I would take that 2.38 and I would need to do the math. 2.38 volts peak times 0.707 will give me a volts RMS of 1.68. Whereas if I needed an average voltage, 2.38 volts peak times 0.637 would give me a volts average of 1.5 volts. I have now uncoupled my BNC connector from my oscilloscope coming from my SIGGEN. And again, it's sending me out a 5-volt peak-to-peak voltage. Well, if you recall, when we measured the actual peak value on our oscilloscope, we determined that the volts RMS was 1.68. This is a true RMS voltmeter. Let's see how close it is to that RMS voltage. At 1.67, we're pretty close to that 1.68. Now, it's not as exact as our oscilloscope, but it's giving me a pretty accurate measurement. And when we take those measurements, well, no matter the type of waveform we have, whether it's sinusoidal or square or triangle, and let's see, can we do a sawtooth? I don't think I have that capability. Ramp might be the closest, but that's still pretty triangle. We could do a positive ladder. There goes a sawtooth-ish shape. No matter what type of waveform we have, we still do those peak-to-peak, peak measurements, volts RMS measurements, and volts average the exact same way. Another introductory concept that's important for us to cover is frequency. Yes, when we are talking about AC, it's always in respect of time, which means it's always in respect of a frequency as well. This picture kind of depicts the half and full wave cycle of a frequency. The positive half cycle occurring between 0 and 180 degrees, and the negative half cycle occurring between 0 and 360. That is considered one full cycle or period in time. The second period occurring immediately after in time. Frequency measurements are often an essential part of preventative and corrective maintenance for communication and electronics equipment. Frequency measurements in audio frequency range can be made by the comparison method or by a direct reading frequency meter. Why you see in my office, often I use a frequency counter or my oscilloscope to make frequency measurements. Frequency comparisons can be made by the use of calibrated audio frequency signal generator in conjunction with either an oscilloscope or a modulator and a zero-beat indicator device. Direct reading frequency measurements can be made by instruments using series frequency selective electrical networks, bridge test sets having null indicators, or counting type frequency meters as mentioned. Frequency measurements for radio equipment are made during tuning, preventative maintenance, and corrective maintenance procedures. The type of test equipment selected always depends on the frequency that's being measured, the required accuracy, and the amplitude associated with that frequency. What that means is, if my measurement device could only measure up to 1 kHz, but my signal is 2 kHz, my measurement device cannot see that signal. If my measurement device can measure a 1 kHz signal only up to 2 volts, and that signal is greater than 2 volts, well, then again, I wouldn't be able to use that device to make an accurate measurement. And then, the last part of that accuracy that we mentioned, if my measurement device is only as accurate, say up to 1 kHz, and my signal is 1 kHz, then it's potential that what I'm seeing as displayed on my oscilloscope could reproduce something that looks more akin to 2 kHz. But the tech order said that I need to be in an accuracy of, I don't know, say 5/10,000ths of a hertz. Well, if I can't see down to that level, how can I get to that amount of accuracy? Again, three things are very important. In addition, the relationship between frequency and periodic time are represented by the following equations. You just simply take the inverse of either. So if you measure something over a period, then the inverse of that period is going to be the frequency. You make a measurement in frequency, then the inverse of that frequency will be your periodic time or periodic measurement. It truly is that simple. Let's demonstrate it. For this demonstration, I'm again using my SIGGEN and my oscilloscope. However, this time I'm going to make a manual measurement. And I'm going to change the type to frequency, or time actually. Now, already displayed on my oscilloscope, it shows the frequency right there at 1 kHz. But will a manual measurement produce the same result? Well, in order to make that manual measurement, we go from leading edge to leading edge. Now, unless specified otherwise in, say, a technical manual, you generally make measurements from leading edge of your signal to the leading edge of the second time period. The trailing edge, didn't mean to make it smaller, would be on the downward slope. So say from here to here. But when I measure from leading edge to leading edge, probably bring this one down just a smidge. We can see that our time, i.e. that delta t up in the corner, is 1.01 milliseconds. And or 0.01. If I was to take the inverse of that, it would come out, as you see here, as 99.5 hertz. So we're pretty close to our 1 kHz signal. Likewise, if I was to take say 99.5 or 99.5 hertz, take the inverse of it, it would come out to something relatively close to 1005 hertz. So yeah, there's a bit of slop within our oscilloscope here in a manual measurement, but it can still be done. Alternatively, you can also select all measurements and go voltage on, channel 1, and time on, and you can get a wide range of measurements there. Well, needless to say, when we start getting into the principles of AC and frequency, we open up a greater world concerning electronic principles and fundamentals of electrical engineering. In application, learning about tuned amplifiers, oscillators, which we built our first one at the end of our DC circuit series. We also have application for detectors and filtering circuits, plus having to understand the type of test equipment necessary for making a measurement is determined by the frequency, the power level, and required accuracy or tolerance. Allowable distortion and even modulation requirements come into play when we get into AC circuits. When we come back to this section, or this series rather, we will continue learning about AC circuits, and as far as containing pure resistance only, and then AC circuits with pure inductance only, and AC circuits with pure capacitance only. So stay tuned for that next video as we continue on in this series. Thank you, Patreons, for being a member of this Patreon, in which I put on. Hopefully you've enjoyed this training for the day. Take care and goodbye.
Mark?